All right, let's get some music on. Da, 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 da. Peaceful piano. Recent music to code by. Let's go shuffle. That's loud. There we go. Let's head over to my channel chat. Create a dashboard. Stream manager. Okay. Okay, I'm just going to poke my friends to tell them I'm live. Da, 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 da. I hate that Twitch penalizes you for linking your Twitch stream. It's kind of lame. All right, we're in Do Not Disturb mode. All good. Okay, so I am currently in the process of switching the local APIC timer initialize method. Sorry, I completely sidetracked there. So we're in the middle of calibrating the local APIC timers, and I'm currently turning everything into a non-interrupt based measurement. So I've created this other HPET sleep counter that doesn't rely on a one-shot interrupt firing. It reads the main counter register after calculating what value we're looking for in that counter. So that gives us a non-interrupt based sleep. And then what I want to do here is during the timer initialize, I want to do a interrupt less measurement. So I'm going to disable interrupts while I do this measure and then turn them back on. But because I don't know what state the interrupts are in, I guess I can... Yeah, I kind of need to create some helper functions, so like set interrupt state enabled, and then we can just say if it's enabled, we're going to do enable interrupts, else disable the interrupts. And the reason we want this is because I'm going to be using this function. Bring this guy up here with the others. So I'm going to call this interrupt state. And that can be set interrupt state. So I can go from this disable enable, and I can do kind of like state equals interrupt state, and then call disable. And then on the enable, I can do set interrupt state with the old state. So what that stops us from doing is it stops us accidentally turning the interrupts back on when they shouldn't be back on. So we might be detecting here that the interrupt state is off. So calling disable kind of just guarantees that we're being disabled. But then when we go to turn it back on, we can't assume that they should be on. So we just give it the old state, which may be off. So it's off, off, or sometimes it'll be on to off and then off to on. So we respect the state. Um, da, 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 da. Oh, what's kind of sucky? Are you there, Fly? Can anybody hear me? Fly Mario, are you there, friend? It says my mic is transmitting. Um, I guess I can change this. Um, we want to be a bool, returning that state, and now We've kind of simplified this. Yeah, that's better. That's the interrupt state and returns the state of interrupts before the change. Okay. All right, so that has now changed things. So we've got this new HPET sleep counter for 100 milliseconds, which is non-interrupt based. We've got the interrupts toggled off. So that should guarantee a pretty accurate timer measurement. I can't think of any better way to do that. One thing I have to apologize for is that because the stream is now an affiliate stream, I've got a feeling Twitch are going to try and milk money from us by playing ads without my knowledge. So I think people are going to start getting ads that I can't control. The only power I have is not scheduling them. So I don't know what behavior that gives you. But you'll have to just let me know, Fly, like how often you get the ads. What's weird is I found out yesterday too from the affiliate information was that if people have Twitch Turbo, which I do, when you're in somebody's stream and that because you have Twitch Turbo, you're not getting ads, but your presence in that stream as a Twitch Turbo user is giving that streamer money automatically with you just being in that stream. And I didn't know this until I read the terms. It was like, you're eligible to earn money off Twitch Turbo users being in your stream. And I'm like, oh, nice. Okay. I didn't know that was a thing. But yeah, I shaved. I can't stand going to hairy. So today was a shave day. Okay, so let's give that a kick. So there's my timer. What I've done is cleared the screen because I don't want the scrolling to happen. So here's a time. Now it's not like perfectly in sync because they started at different times, obviously, but as long as it's kind of like, I don't know, I think I'm gonna create an internal counter by milliseconds. I don't know if that's a bad idea, but I'm gonna try it for. What's the timer for? Oh, this is just a web page that is telling me the current time. And I'm measuring it against those log lines in the console because there's no other way for me to measure to make sure that my timer function has truly measured 1 second unless I compare it to something else. Right, so this ticking here needs to be a 1 second timer. But yeah, the OS does not know what the current time is. See, what happened there was, see how the tick pauses? It's because I stopped moving my mouse. It's so weird. But I don't trust the frame buffer. Like, I'm judging this from the frame buffer, right? And I don't want to do that. So I'm going to make an internal clock. That ticks a timer by 1 millisecond. And then I'm going to create a console command that on demand queries that value. And then I can do like a 30-second stopwatch and see if the actual time in the background is definitely measuring like 30 seconds, right? I could even make a sleep command, but that won't help because it's not based off the LAPIC. You know what? I should put this. I should put it here. And then this. I'm just going to make that go away, that log line. Do, 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 do. Is the music okay, by the way? Oh, another thing I did earlier when I wasn't streaming is I set up the ability to use gdebug. So what I can do now is I can set breakpoints inside of the OS image and set those breakpoints on any line, and then I can inspect memory. Basically just a normal debugging stuff, but it's pretty handy now that I know how to do that. For anybody that wants me to show you what I did for that, all I had to do was make sure that my image was compiled with debugging information, which is a flag on the compiler, which is these two, G and G debug. And then I start QEMU with two flags, so a lowercase s and a capital S. The lowercase s means open a gdebug server in QEMU, and the capital S says don't start the kernel until the debugger has attached and continued. So it starts in a breakpoint state, a paused state. I can show you what that looks like. So I've got to make a debug command here now. And here's the QEMU saying it's paused, guest does not initialize the display. So it's waiting for the gdebug session to attach, which I can do here. And I can say target remote on that port. And now the gdebugger is attached. And then if I hit C for continue, the OS now runs. And I can break it anytime and inspect registers. So I can do this here, and I can do info registers, and we can inspect things at memory locations. So it's a pretty handy thing to have. So yeah, let's finish off doing things with the timer. So what we shouldn't do is just assume that every processor that we initialize is going to have this timer. But for the Bootstrap processor, we should set it up. So what I'm kind of thinking about here is when you fire up 8 different cores on the CPU, each core has a unique frequency, which this timing method captures. But what we don't yet have is a system that lets me capture state per core and set that information inside the core. So ideally, what I need to create is a struct that contains CPU level state, and then create an object for each core or allocate some memory for that struct for each core, and then put that pointer to that CPU state into one of the, I think it's the FS and the GS registers. So the custom purpose registers can hold the pointer to that. So then when the cores are running, and they need to do things with their timer, which is a unique frequency, they can look into that state bag and go, okay, there's my timer frequency, and now I know how to set up 1 second's worth of time for this specific core. But we haven't fleshed out the whole multi-core stuff yet. So I'm going to kind of just hack this timer function here to just start the periodic timer. In 1 milliseconds. So let's do timer in 100. So we'll just divide that by 100. So that'll get us a 1 millisecond timer. So what we can't be doing now in our timer function, which by the way, I don't know if anybody's here from yesterday when we were having problems with the page faulting. That was the cause of having a built-in function here. It was the unreachable built-in, which I think I'm using somewhere else. Yeah, so when I had this inside the ISRs, it was messing with the compilation of those functions, and that's what was causing a page fault. So having removed those, we don't get the page faults anymore, which is cool. And yeah, so that was, part of yesterday's bug. But here's what I have to learn, is when I'm in an interrupt service handler, I can't be doing, there's a couple of problems still left over here. I shouldn't be doing this manual ISR save and restore. That's pretty naff. And I shouldn't be doing frame buffer stuff. So the kprintf, the kernel print to the console or to the terminal, and that's just horrible because that's invoking frame buffer manipulation. So in a very high firing interrupt, you do not want that to be happening at all. And I don't want these function jumps either. So I need to wrap this up into one of these kind of scripts. But I'm not too worried about that for now, because that's not causing a performance problem. So again, got to be careful with multi-core stuff. So what I'm creating here with an ALPIC or a LAPIC timer that's firing in context of the core, I've got to be careful not to have multiple CPUs firing down this function and modifying state that's only specific to the BSP. So whatever I'm doing now is going to cause me a problem in the future, but I'm fully aware of it, you know? So I'm going to call this timer MS. Incrementing timer in milliseconds since the kernel started. We're going to say this is a volatile because it is. Modifying it and reading it from different cores is going to be volatile. And then in the LAPIC timer, we're just going to increment this variable. That's its sole job. And then kind of don't like its name though. Kernel timer. MS maybe? And the reason I want it to be that is because in the IDTH file, and again, this is a temporary thing, but it is what it is, you know? How do I... For a second now, I was thinking about how do I expose this, but it's just an external. So defined here. So it's incremented in the ISR. Now we'll create a terminal command over in the terminal source. Boop. This is still a bit crude, but it is what it is for now. It's just the kernel console. It's not going to be the user state level console, so fine. So we'll just call this time. Kernel timer, and it's in IDT. Do we have... No. See, it already feels wrong bringing in the IDT for that timer variable when it's something to do with the kernel. Like it's a kernel state variable, but it'll get removed in the future. So it's an LU. Whoops, and it's in milliseconds. I'm going to create another command called time. I'm going to call it S time. And I want to divide that by 1,000. That's weird. Why does that have double brackets and this one doesn't? Because the bracket's missing there. Syntax error. Okay. Conflicting type qualifiers for kernel timer volatile. Oh. Oh, not you. It's going to be in the H. It's an external volatile, uint64. There we are. So, a really high firing interrupt now is happening in the background. Again, I don't know if this is a great idea because this is going to be driving QEMU crazy. Like, how is it handling such high throughput? But, so, we'll ask the console. Oh no, is it bricked? Have we killed? Oh, I've turned off the PS2 initializer in the kernel from my debugging earlier. There we go. So time. Oops. Yeah, I've got a feeling that this is just getting hammered. S time is 1 second. Hello, Exploding King. I've got a feeling that the bootstrap processor here should not be it shouldn't be firing a 1 millisecond timer. Seems a bit excessive. So let's turn the timer down to a 1 second timer. Times that by 10. Put that in seconds. Thanks for the follow, Mr. King. Just smacked my mic there. Sorry about that. So I'll change this to seconds. Okay. Now eat the mic. It's a bit crunchy. And I'm not that hungry since I ate before I turned the stream on, so maybe another day. Skill issue. I've just realized who you are, Victoria from Twitter, right? Let me click on your profile. Do I recognize? Oh, it is. Hello, Victoria. How you doing? Thank you for stopping by. Um, yeah, you're witnessing my insane journey into OS development. And 3 months in, I'm still feeling like a bit of a noob. What's a LAPIC timer? So a LAPIC timer is there's a circuit on each CPU core that iterates at a certain frequency. And we use that circuit to measure time. So what that gives us is a timer per CPU core. Now the LAPIC stands for Local APIC, and it's kind of like the logic chip that supports the core inside the processor that handles things like interrupts. And we manage the timer stuff through the LAPIC, the Local APIC. If I can find you a diagram. Here's a good diagram. This one on the right here. So the CPU block here is the CPU core, and you have one of these local APIC managers on each CPU core. So interrupt management per core, and it gives you the information about the timers and the frequency of the core. And then you've got this master IO APIC, which is something else I refer to often because we have to utilize that, but also doing interrupt management across all the cores. So every interrupt, we can read the number of operations the CPU has done since the last interrupt. Not really. We're not measuring. Well, no, now that you ask that question in that kind of way, I think it's kind of like the maximum speed that the core can execute interrupts. So it's rather a huge number, the way it's timed, or the ticks, if you like. And I do think it is something to do with the amount of interrupts it can process per second. I'd have to check the hardware docs for that though. But the way we're measuring the LAPIC timer, so that what's really difficult in the whole context of those timers across the cores is that they're all running at different frequencies. So every time you bring a core online, which is like a thread that you can control, like when you do multi-threading in any other language, you can think of it like that, right? The core comes online, it starts running code in memory. It's a separate thread of operations, but its circuitry, its timing is different to every other core. So every time you bring a core online inside your kernel, you have to measure that circuit independently of all the other cores and store that frequency somewhere so that you know how to measure time on that core. So if you ever have a situation, for example, where somebody writes a program and says, sleep for 2 seconds, right? Depending on what core you're executing that code on, you need to know what the frequency of that core is to correctly measure 2 seconds. So yeah, I mean, it's not simple. It's kind of like, it's a pain in the butt setting it up, because to actually measure the circuitry inside the cores, I have to use another timer, which is a crystal-based chip called a high-performance counter, which you may have heard actually. So the HPET is another counter, but it fires at absolute insane speed. So this timer fires at something like, oh, I can't remember. It's like millions of times per second, if not more. So if I go onto Wikipedia and find this table, It's actually firing at 1/4 of a second, and it's the pulse time on the fastest laser. So we have a chip that gives us a measurement of up to 1/4 of a second. The cores don't give us that, but we use that high performance chip to measure how fast the cores are going. So we first, the kernel initializes the high performance timer, measures how fast that thing is ticking, and then we utilize that guy to measure the cores. And that's what we've been doing for 2 or 3 days now. And we've just got to a point where it's all working, which is really cool. Reminds me of a while ago when I was making a very thin OS to run an SDMX DB driver. Before things like lambda expressions exist, etc. I think kernel in C++, LAPIC, I think, HPET, have to load up, of course, the PIC or the APIC, yeah. I think these support chips, I don't know what they physically are on the CPU, whether they're external to the CPU on the board somewhere or they're actually under the CPU casing. I don't know, but they seem to be common between every kind of CPU that I've seen, like AMD and 0886 processors and stuff like that. So yeah, that chip is on most boards, yeah. They used to be part of the North Bridge. I think I read in the documentation that they sit on the South Bridge. Well, the high performance chip sits on the South Bridge somewhere near there, because you can actually set it into a mode where you can ask it to fire interrupts down the front side bus and directly into the CPU, bypassing the APIC controllers. But I've not seen anybody programming with front side bus interrupts. So the whole concept of interrupt management in OS coding is quite intimidating. And I feel only about 75% comfortable talking about it. So interrupt lines, input lines on the LPIC, or the IO APIC, should I say. And then there's CPU core level interrupts, and you can there's like mapping tables that can override them and redirect them. It's kind of complicated. So coming back to this timer. So I'm not comfortable firing 1,000 interrupts on this bootstrap processor per second. I feel like it's like a really bad design. But let's see what it does with the 1 second one. I've got a feeling that's going to be fine. I can probably get rid of the terminal clear now. So we were doing a clear here because once you get past one full screen of text, your frame buffer requests get quite expensive because you're scrolling the screen. So that's the time command reading that timer now. So you can see that counting almost in 1 second increments. Yeah, so it seems to be, I mean, the other thing I have to consider too is that we're compiling everything in debugging mode. Like QEMU is in debug mode, the kernel image is in debug. I don't know if that has an effect. I don't know what the throughput of interrupts is normal in a kernel. at all. Like, at some point, you do want something tracking inside the kernel that is a millisecond. What's the word I'm looking for? The resolution is in milliseconds. Unless, do you though? When do you ever deal with milliseconds in time? It's only when you're measuring code blocks with a performance measuring lib, or no, you must do, because like when you call datetime.now and you get ticks in milliseconds on Unix, that milliseconds timer has to be ticking from somewhere inside the computer at the kernel level. Like nothing in the chipset or the CPU is managing an ever increasing number in milliseconds. So it's a kernel level tracking thing. But yeah, when I was in the OS Discord to the guys that have wrote OSs themselves, they mentioned that I should be okay with, like, perfectly fine to have 1,000 interrupts per second coming through the kernel. But as you saw when I tried to do that, QEMU basically logs every interrupt that comes through the system. So it's probably trying to log 1,000 interrupts and read from all the CPU registers, dumping all that information in the console. I don't know whether that was holding it up. So yeah, I mean, it's job done though, right? I've got the LAPIC timer has been initialized correctly to 1 second. So that goal has been met. So ideally, when the CPU cores come online, they're going to initialize the LAPIC, but they're not going to start the timers. I think the timers are going to be request only, but then I probably need to do some research on which kernel core manages like that timer thread. Like, does it go on the Bootstrap processor thread, which is like your main startup kernel thread? Or do you offload it to one of the other cores so it's out of the way of the kernel? Probably what happens. So now coming back to where we were headed, so our long-term goal is we want to get into user space. So at the moment we're in kernel mode, right? Everything is in what we call ring 0, the highest privilege, where all your instructions are being ran against physical memory and you've got full access to all the devices and you can do anything you want. But we want to get into user space where we're going to start developing mini programs to run and execute on the cores. And then we'll have a scheduler that manages the threading and the process starts and pauses and sleeps and all that kind of thing. So time slicing. But to get that, we need a file system because we can't load a program else, right? We need something on disk to load and execute. So to do that, we need a file system driver. And FAT32 is probably one of the easiest that you can dev. It's probably well documented, given how old it is. But yeah, so you can start doing different file system drivers. You can read Linux ext2. I have no idea what's more difficult than the others. I imagine whichever you choose, so we're going to choose the FAT32 one because that's what our kernel is built in. Or should I say the image that we're loading into VirtualBox is built on a FAT32 drive. So it would be nice to package pre-compiled C programs in that image and then be able to navigate to those files and load them. So FAT32 is the obvious starting point for me. But yeah, so there'll be a challenge to reading files and then writing. So mutating the state of the drive. Oh wow, it's got literally almost every file system documented on here. Amazing. But it looks like once you've done FAT32, you can probably support FAT16 and FAT12. First step is memory paging. Oh, memory paging? That is, to me, that was really fundamental. I didn't feel comfortable developing in the kernel without some memory management. So we do have a memory manager. And that's in here. And it is a page level allocator. So pages in RAM are 4K blocks. So when I do the weakness of this allocator at the moment is when I do a malloc, which doesn't exist yet, we have what is called a kernel level malloc, what we call a kalloc. So this one, but yeah, so at the moment I can ask for a block of memory. It doesn't matter how big that is. I just ask for that size number. And it does a divider based on the page size of 4K blocks. So the weakness of it is if you ask for 10 bytes, it's going to give you a 4K allocation. And if you ask for another 10 bytes, it's going to allocate another 4K block. So in effect, you've got a big memory hole of 4K minus 10 bytes in between your first allocation and your second allocation. I'm not sure from a memory allocation strategy if that ever goes away. Like, I don't think you can do things at byte level. Like, you need some kind of divider to be efficient. So yeah, we've got this calloc, right? So this code I wrote week 1 of the kernel's development. And it's really simple. It just runs over the RAM, looks how large the RAM is, chunks it all up into 4K blocks, sets up a bitmap, which is just a huge array of bits that indicate whether that page is being consumed or not. And then when you come in and you calloc and you ask for some bytes, it'll look through that bitmap and say, okay, what do I have free for that amount of memory? And then it'll allocate you a contiguous space of pages for what you asked for. Now, a layer on top of this what you see in Linux and what you see in other operating systems is there's better allocation strategies called slabbing. And that's just another layer on top of what we call a page manager. So this is a page manager, the most core allocation routine that you can do. But when you get into user space programs and they want efficient memory allocation and fast memory deallocation, you want a slab system. So at some point in the future, I need to iterate over this memory manager and implement that slab concept over the PMM. So this is what we call the PMM, the physical memory manager. And the slab system is kind of like a virtual memory manager, where if you run out of space, it will probably start leaking into hard disk memory mapped files, for example, like a page file, but it's invisible to the user space. So concepts like that need plugging into the kernel at some point in the future, but we can delay that. So as long as we've got this PMM, as long as we can grab bytes from RAM, it's good. We don't even have a free method implemented, so I can't even deallocate the memory. But as the kernel's developing, it's like it doesn't need to deallocate anything. Like everything on startup is about, I need to create space for recording things, right? So everything's about just allocating and reserving memory at the moment. So it does what we need it to do. So yeah, it's we get into doing the hard disk driver. Obviously, we'll probably need to store things like table, MBR stuff. You know, we're probably going to have to cache some metadata around what we're doing with the disks. And to do that, we're just going to lean on the calc, the PMM. But it's kind of exciting. I get excited thinking about it's kind of a nerdy level excitement, right? I think to myself, okay, we're going to do a FAT32 driver, right? So what's the point of which you look at that and think, oh my God, I can see files, right? So I think the very moment that I can parse that structure on disk and actually see folders and files in a table somewhere in memory, it's like opening your eyes, you know. It's like, oh my God, I can see data. And it's a big dopamine hit doing that. That's kind of what I love about OS coding at the moment is you get these little problems. Well, they're not little problems, you get these big problems. And there's excitement on solving them. So, FAT32. Supposedly written by Bill Gates, FAT is a very simple file system, nothing more than a singly linked list of clusters in a gigantic table. FAT file system uses very little memory unless the OS caches the whole allocation table in memory, and is one of, if not the most basic file systems in use today. Nice. FAT12 was designed for floppy disks. FAT16 was early hard disk sizes, and FAT32 was Windows 95 and 98. I think it was NTFS, right? I think NTFS was the switch over in Windows 2000-ish when they went to the Windows NT kernel. Is NTFS here, or does... Ah, yeah, it's got it here. It's Windows 2000 NT5 added this to Win32. I'm assuming that just added support for like humongous level drive sizes. It's kind of, you take the 4K base slices you have for the memory pages and the metadata, store file name and how many more blocks follow, etc. Yeah, exactly. So if you, for a memory manager, if you're storing metadata about what things you have allocated and where in memory, that is you taking up physical RAM to record that metadata. So in my memory manager code, part of its initialization is allocating a chunk of RAM devoted to that metadata. So there's this function here called create page bitmap. And like this comment says here, now we know how big our page map needs to be, depending on how much RAM I have. Let's find a spare place in memory to keep it. So I go hunting for a free page in memory that's big enough to store that bitmap, and then I allocate it, and then I take that reserved space away from ever being allocated in the future. It just becomes a big reserved block of memory. So what you have to remember is that the more elaborate your memory manager becomes, the more, virtualization you're putting on memory and more state that you need, or more metadata that you need to store for those blocks of memory. You're creating an initial payload or a footprint in that memory block. So you might say, this memory manager X, for every 1 gigabyte of RAM, you need 100 meg of metadata, right? And somebody else's memory manager will be like, well, I only need 10 meg, right? And that's when you kind of see sometimes in a Windows system how you'll have 4 gig of RAM, but only 3.76 is available. Because it was all metadata, and not even just metadata for your memory management. One of the things I learned when I came into OS Dev was all of the devices in your system. So, I don't know, the LAPIC, for example, the IO APIC, the HPET, there's a huge, massive database of BIOS configuration, and all of that is reserved in RAM. And some of those memory locations act like CPU registers. They're volatile pieces of data. So how typically you think about RAM, and you think, okay, RAM is a static, or rather it's a dynamic memory bucket, and what exists in there is what I put in there, right? Not true for some of the locations, because the other devices on the motherboard have laid claim to those memory locations, and they're happily doing stuff in the background and modifying that RAM location completely outside of your OS's control. Like, it's nothing to do with the kernel, it's nothing to do with the BIOS or anything else on the motherboard. That device or that chip has reserved a very specific location in your RAM block and is using it all the time to push and pull values to and from it. So when you read information from those memory locations, we call them volatile because we just don't know what value could be in there at that point in time. And just because you read it at one point and then read it directly again after doesn't mean you're going to get the same value. And that's a lot. So all of the concept in OS Dev, when you're talking to devices or you're looking at chips, you're actually just poking around on your own RAM, looking for the reserved blocks that they've located on. And then they take instructions from those locations too. So like they're sitting waiting for you to put a certain byte value at a certain location in RAM. And when you put it in there, it clears it and uses that as an instruction to then go off and make the device do something. So yeah, it's super interesting seeing all of this, right? So if I show you the HPET source code, all of the structs at the top of this code block, they're all marked as volatile. So it's the C keyword volatile. It's telling us that, okay, this pointer is looking at somewhere in RAM, but somebody else is controlling that value, right? Exploding King, you are my first subscriber. That is crazy, dude. Thank you so much. Yep, I only got my sub button last night. I've only been streaming for a few weeks, so sub button got activated last night, and that's it. You're the first sub. Well, thank you. You now have the founder 1 month sub badge. Yeah, that's the kind of what I was hoping to do in a soonish fashion. Is I wanted to start coding on a scheduler, and then I realized that there's just a ton of more preliminary steps that I need to take before I get to doing a scheduler. And a lot of learning too, like there's a whole concept in the Intel manual that you have to learn on how to configure the cores for task state switching, and there's a whole bunch of domain knowledge that I need to learn up on there. But yeah, the scheduler is really fun to think about. You know, like Hello World scheduler is a round robin. I've got 8 cores, I've got 8 processes that I want to run. And, you know, you just round robin the cores to each process, or, you know, everyone gets an equal time slice. But in a more real world, you have high priority threads and you have low priority threads. You have high priority kernel background tasks like IO, and you have lower priority. So yeah, schedulers, again, you could spend your life working on scheduler algorithms, and there are tons of people's ideas on how schedulers should work in very efficient ways. So it's going to be fun to get there, but I kind of want all the things around me. You know, I want my devices of, okay, I want to be able to read and write data on disk. That would be huge. I want to be able to read, allocate and free memory from RAM. And then I want to fire up the cores, and I want to implement running programs and scheduling the core time, which then invokes the scheduler. So I can't wait for that stuff. Man, the way it described this FAT32 being just a single linked list, I'm kind of excited. Implementation details. Okay, it's a flat array of clusters. The physical media does not address its data as a flat list of sectors, really old hard disks and floppy disks. Then the cluster numbers will need to be translated before being sent to disk. Got 3 main areas: the boot, the FAT table, the directory and data area. Okay, so we know where the boot record is because that was the bootloader's job. Oh, one thing so I'm still probably a couple of steps ahead of myself. Before being able to read and write from a hard disk, is I need to know how to communicate with that device. So I need to kind of check on how we initialize looking for the devices on the motherboard. So how you need to think about it is that your hard disks are connected onto the motherboard at some location, and you have to navigate down the PCI bus looking for devices. And then once you've found one, you kind of got to ask it a question like, oh, hey there, are you a hard disk? Are you a storage device? And then you kind of need to query that information. And once you know you're dealing with a storage device, and you can make the assumption, oh, it's a disk drive, right? And now I can talk to it as though it's got operations and instructions to read and write across its sectors and clusters and whatever. So we might have to do some preliminary work before we get into actually communicating with the hard disk that is attached in the emulator. But it shouldn't be too bad. Should not be too bad at all. Boot contains both code and data mixed together. The data isn't coded as a PPP. Okay, so if what I'm kind of looking for in this table is like, is there a signature you can hook onto? Like you're going to want to hook into a specific location on the disk and go, are you in FAT32 mode? Or are you a FAT32 formatted disk, you know? But this all looks like number of FAT tables, root directory entries, total clusters in the volume. This byte indicates the media descriptor type. Oh, might be this. Yeah, so that's a table telling me what the device type is. Number of sectors, sectors per track, heads or size of the storage media, hidden sectors, the LBA at the beginning of the partition, large sector count. Okay, note the geometry of the media, sectors per track, heads, and perhaps the number of bytes in each sector is not necessarily known correctly by the program that originally formats the media. The new BIOS may specify a different geometry for the same media, so it generally is a very bad idea to put the SPT or the head numbers, or to trust the SPT or the head numbers. Get them from the BIOS instead. So you are tricked into thinking that a hard disk is just a big array, and it isn't. Not at the driver level. So you do talk to it in sectors and clusters and blocks and stuff like that. Extended boot record information comes right after the BPB. It contains different information depending on whether the partition is a FAT12, FAT16, or a FAT32 file system. Drive number, flag, signature, volume ID, volume label, system identifier, boot code, and bootable partition signature. Another signature here, there's a lead signature here. These signatures are really handy because when you make your like memory parsing code and you find those signatures and you verify the values on them, you're like, okay, I'm here. I'm at the right location. So they're very handy. exFAT the whole boot record was created from scratch of extending the existing boot records even further. You can recognize exFAT by noticing that in the boot record, the bytes per sector is 0. Sector, cluster, drive select. Cluster, heap, offset. To read the file system, find out how big a sector and a cluster are. A sector is 1 left shift sector shift bytes. A cluster is blah 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 bytes, and find the start of the fat and the start of the cluster heap. Note that the first cluster is still cluster 2. And the fat table indicates the status and location of all the data clusters that are on the disk. It can be considered the table of contents. Yep. The fat allows the operating system to follow the chain of clusters in a file. The table value is greater than or equal to blah blah blah. Then there are no clusters in the chain. This means that the whole file has been read. Bad clusters. Okay. I wonder if bad clusters is a hardware level thing. Like it's good at finding bad areas of the disk and telling you you can't use this. Entry is reserved for future must hold written out to the fact case is fully contiguous. The fat table is not used for allocation status of a cluster. Instead, there's an allocation bitmap to handle that. The directory entry simply stores the information needed to know where a file's data or folder's children are stored on the disk. It also holds information such as the entry name, size, and creation time. There are 2 types of directories in a FAT file system. There's the standard 8.3 directory entries, which appear on all FAT file systems, and the long file name entry, which are optionally present to allow for longer file names. Okay. So that's a bit of metadata. The long file name entries are always placed immediately before their 8.3 entry. That's exFAT. No, we don't need that. It's a stream extension entry. It's called an extension, but it's 100% required to exist directly after the file entry. Reading the file, the second bit in the stream extension is only flags indicate if it's stored as extend. If you need to use the fat table, if it's set, the file is contiguous, and the fat is not up to date. If it's clear, the fat is accurate, it needs to be used, but still, could still say it's contiguous. If you find an entry in your IO journal that doesn't have a closing, then you have to rewrite. Oh, sorry. If there are some some techniques to make sure that data doesn't get corrupted. So when you start writing to the FS, you record in a journal that you started writing, and then you have to check that you stopped writing. I think what you might be referring to there is, what if all 8 cores wanted to do I/O on a hard disk? Do they stack or queue? I don't know. We're talking like low-level details that will definitely hit, but I've not yet seen in an implementation. As soon as I see the documentation of how we talk to a hard drive device, it'll probably tell us there, like, this is an atomic operation, right? Because it will be quite obvious that you'll be coming into that device with multiple cores and wanting multiple operations on it, and it might just go, you can't do that. It's like the PS2 driver. So when you're doing things with the keyboard or the mouse, it's very serial. You can't multi-core it. You have to send it a command to a specific area in RAM, wait for a signal, and then when it signals, it's ready for you to read information from another area of RAM. And you kind of have to batch requests up and queue requests. But yeah, we'll definitely get there. This is all, I'm skimming over this to kind of give myself an expectation of how big this thing is we're going to write. So everything I'm hearing about this at the moment is just meta, like metadata here, metadata there. So like here, okay, programming guide, it's giving you all the structures that you need probably to just copy and paste into code. It's not obviously telling you how to execute reads and writes on a device, because that's probably a different document. Yeah, and I bet there's some kind of ACID compliance at the hardware level. Like if I ask a hard disk to go and write 32 bytes, it's probably not me managing that low level, byte by byte writes on the disk. There's probably enough in the controller logic on the hard disk itself to tell me whether that succeeded or not. It would be way too low level to do that. I mean, we can have a poke at another open source operating system and just get a look for the kind of functions they have and the interoperability, like the device communication that's going on, and just see if there is a mention of journaling in there. But that would seem crazy if you had to do that. So yeah, this doesn't look too bad at all. Like, it's not terrible. Like, it's a bunch of metadata. There's a bunch of calculations on finding where your stuff is. There's some validation and signature testing. After the correct cluster has been loaded into memory, the next step is to read and parse all of the entries in it. What I'm kind of wondering is, do you have an area in RAM where you've kind of no, you wouldn't have done that. So many questions are firing in my head about the implementation of this, but it's all going to come out in the wash when we get to the actual detail of doing it. Like, I'm thinking if somebody asks for a file open command, right, with a specific directory name, do we then open the device? We start walking down the FAT table looking for that entry. So we do an index scan on the FAT table. And then we navigate down to the data cluster and fetch the data. Or do you keep like a shadow copy of the FAT table in RAM? Do you even not need to do that because it's fast enough doing it with a disk anyway? You know, lots of questions there, but again, it'll come out in the wash. Wish this wiki had a dark mode. I can feel my eyes burning from the white on this web page. Following cluster chains. Reading extent, so that's the exFAT file system. Typically during development, you want to create a disk image with a FAT file system. There are two common approaches for this, either by using a utility that works directly on images or by using a loopback device and using the OS owned driver to work on the image. Oh, that's just telling you how to get yourself a hard disk initialized image, which we already have one with our build scripts. So I'll build HDD, this guy here. We're using M format, a Linux tool for creating that FAT32 disk. So we'll literally have a FAT32 initialized disk ready to read from, which where is our kernel is living. So there's a page here, intro into sectors and addressing. Heads, sectors per track. Right, so we're going to try and now hunt for some kind of page that tells us how we actually get to that drive. So I wonder if there's something on the main wiki. Where's the kernel code being stored? It's being stored in a FAT32 image. So what happens is you create a disk drive. It initializes the bootloader at the bootloader location. And then it sets up a FAT32 volume with the kernel source code loaded into that FAT32 volume. And it uses the UEFI chip. So UEFI is a motherboard chip that came, I can't remember when that was released. It's been around for a while now. And it's a new style of BIOS or a booting sequence, and it has a ton of support in that chip. So that chip itself knows how to read from FAT32 drives, which is pretty cool. So the bootloaders depend on using that UEFI chip to read from the FAT32 image where our kernel lives to load it into RAM. And then once it's got the kernel into RAM, it boots into it just by making a jump to its location to start running the code. Thanks for that follow, Rebel. Okay, so that's the actual format of the storage, which sits okay in my head. I love that it's not too difficult. But we want to get to bootloaders. Let's see, where's our file systems? communication devices. So there's another fork in the road that we could have gone down. We could have done a network driver. We could have opened up the Intel 8254 chip and spoke Ethernet frames even before we had a file system, because we can just communicate with that with the terminal. But another concept, sorry, that I need to touch on with the file systems in general is the Linux VFS. So again, this is a way of thinking in the Linux world versus a Microsoft way of thinking about drives and devices. Is like Linux maps everything to a drive, like dev null, dev HPET, dev ACPI. Like it's got tons of different things in this kernel that are mapped to a file system in the virtual file system. So you can code your kernel to have a VFS and do the same thing. You can go in and find all the different kind of devices that you want to mount into your virtual file system and navigate everything as it's a file system. Or the Windows approach, where devices get pinned to a device label like C:, D:. And you have a drive letter. And those drive letters are unique to devices. So two like different approaches to you thinking about your file system. And of course, you've got complete control of not going down that route at all. You might not want a VFS. You might not want to have drive labels for your devices. I remember being, a Windows guy for the start of my career and then going into Linux and being completely dumbfounded by how I couldn't find the C drive. The very first time you go into a Linux terminal as a Windows person and you're like C:, you're like, how do I get to my C drive? It's kind of embarrassing, but I remember that day. So where is UEFI, PCI, USB and things? Oh, it might be in here. Or is it this one, storage devices? Ooh, it could be this one. Describes the oldest hardware mode for accessing devices. Start here for all your driver needs. ATA-PIO mode. There's a TAPI. CD-ROM drives are usually a TAPI. You'll need some ATA parts for setup. If you want to make disk accesses using the legacy BIOS. And a SATA. Okay. So let me just go back a second. What's NVMe? It's a controller. It's 64-bit memory mapped I/O. What's it for, though? Like, whatever its commands, what does it do? I/O submission queue, I/O completion queue. IO commands, read and write. Oh, I think this is a controller. It's kind of like the logical. It's like the logical layer that you were touching on earlier around. You might want to journal. It looks like this is something that handles that for you. And it's interrupt based too. Find PCI function with class code 1 subclass 8, enable interrupts, bus mastering DMA, memory space in the PCI configuration space for the function, map bar 0. Reset the controller config, admin queue base addresses, start the controller, enable interrupts, send the identify command to the controller, check it's an IO controller, record the maximum transfer size, reset, control, blah, 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 blah. For each completion queue, read all entries where the phase bit has been toggled. I still haven't quite grasped what this is. Family of specifications define our host software communications with non-volatile memory across transports like PCI Express is the industry standard for solid state drives in all form factors. Okay. So how does that differ if you know you have like SATA drive? This time of writing, there were 3 supposedly definitive conflicting standards for SATA. It may be best to wait for the industry to shake out a little more completely before trying to write SATA drivers. So that brings me back then to the NVMe. Which controller does the VM emulate? What does that mean exactly? Which controller does the VM emulate? Oh, you mean QMU. Sorry. You're talking about the emulator QMU. So I bet, you know, QMU documentation, NVMe emulation. QMU provides NVMe emulation through blah, 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 blah devices. QEMU emulates version 1.4 of the NVM Express specification. ID is set to NVMM. Do we use that? Let's just check the make file. No, there's no mention there of attaching NVMe. What's that HDA flag doing? I'm just gonna have a nosy. Yeah, I want to double check. So this is the an operating system that's been in development for a long, long time and has most of this stuff done. So it's good to go in here and kind of see how they're doing storage. So like here in their device folder, they have, let's see, PCI driver. So they've got some PCI code there that can scan the bus, I believe. Legacy though, scan function, scan bus, scan root bus, dispatch driver. Terrible way to do this. Try to use MCFG where possible. I'm not sure what that is. So it looks like there's some IRQ routing for the PCI as well. There's these PCI macros, probably reading from memory mapped locations. Get device by vendor, map the bar. Just see what this is doing. Oh, actually, let me open this up in VS Code. Define PCI write D, PCI write device offset value. So it's this function. And it's a function pointer to that. Oh, I see. They're picking between two legacy reads or MCFG. So there's two strategies. How is the PCI bus structured here? I've no idea. So if I look in their header file for their, they've got a struct here for the driver, something called the bar, and in the device, which, to be honest, it's an area on the OS dev that we've not looked at yet. So there's a page on PCI down here. And it's got sections in here, for example, like enumerating the bus, recursive scan, brute force scan. And then there's IRQ handling. MSI is a message signaled interrupt. So that doesn't look too bad. Where are the base locations though? This, like here, it's talking about the base register. Is that some fixed location? Or is it in the ACPI? Do they talk about the ACPI? No, only in the IRQ routing. Yeah, so we probably got to implement this kind of thing because there could be all sorts of devices connected to the PCI, not just storage devices. Like you literally could have somebody with a custom sound card or a custom network card or a custom Wi-Fi adapter that's all connected on the PCI bus. And eventually you'll need to route them and communicate with them through the bus. So you're going to kind of want to see what devices are connected in your system using the PCI scan. So maybe we do that first. Maybe we do like a PCI scanner. So let me just back out of that PCI code and just look at the storage code. So they've got the master boot record entry struct there. They've got a partition device, read part, write part, sectors, block size, partition number. How are they doing that read here? Like, what is root? Resource. Root block device. Oh, there's another layer to this. So they've got FS. Ah, okay, so they've got all the different file systems in here. Yeah, we're not doing anything as elaborate as this one. Like this operating system here has got loads of really abstract systems in. But we can be very specific at the beginning. Like we just need to get some experience on, oh, I found the hard drive, right? And then how do I communicate with the hard drive? And then we just write code for communicating with that one hard drive. And then once we've got the experience of understanding how the detail works, we can then work backwards and start putting abstraction layers in. It would be crazy to start at abstraction levels when we don't even know what we're dealing with. And the people that have developed this specific operating system have probably got way more experience than me and probably new abstractions up front. Um, but like, yeah, they've got FAT32, they've got EXT2. So what they've got here is the virtual file system that Linux implements. So this is that whole mounting of different file systems, different devices into one virtual file system manager. Like here, virtual file system mount. So I bet anything can call this and mount stuff into the virtual file system. They've even got symlinks, just like Linux has. Yeah, so they've got a virtual file system. They've got multiple file systems in there. The FAT32's in there. And this doesn't look too terrible. That's not a lot of code there. It's just all structure building. So that's where I want to kind of have some fun in. I want to get to the point of where I'm reading and writing the FAT32 system. And then what I want to find though is where are they physically getting that device? So if I run to the init function, virtual file system, add file system, mount FAT32. Device resource, read device, VFS node. Yeah, that's probably, we're still in a lot of abstraction here. So there's the PCI scanning. So this definitely feels like the precursor to what everything we need to do. We need to do some PCI scanning code. And then once we've got the devices, so is there any constants in here that give hints to that you're dealing with an IO device? Class maybe? Legacy read. So that legacy read and legacy write is using ports. So the assembly level in and out instructions. And then the MCFG, I'm assuming it's using some memory mapped IO. Yeah, so there's something here, look, where you've got an MMIO base, an offset into the physical memory map. So you've got some memory mapped IO communication there. And with the scanning, it looks like it chooses whether it wants to do legacy mode or memory mapped IO. But we can gather all of this from the wiki. We can just follow the wiki page down on doing this scan. We won't need to come into this code. It's just about getting a feeling for how it's all structured, what the major steps are. So though I'll kind of use this OS source code base for kind of gathering recon data, recon ideas, and domain knowledge, I don't copy or paste anything from anyone's projects in this whole endeavor, because that's the worst thing you can do. Like if you're writing drivers and you don't know what you're dealing with, you've got no chance on debugging them or developing them further if you're just ripping code from somebody else's OS. So it's impossible. So here, look, for example, I can see they are going into the ACPI. And we have code for going into the ACPI. That's just like a library of information in RAM. And it looks like they're looking for a table that gives an indication to whether they can use that updated memory mapped IO or whether they need to fall back to doing the legacy ones. So they set the pointers here to legacy read write, which is the in and out ports. And again, we might not need that. If I find that in QEMU, that we do support the memory mapped concept, then I'm just going to put support in for the memory mapped ones. If this was like a real OS that you wanted to run on different consumer hardware, you would want to look for the support and then fall back to strategies of doing port in and out stuff. But I'm not too bothered for now. So yeah, I mean, we've got a place to start then. And what I still haven't linked up though is at what point does it connect a found device knowing that this is a storage device? I think that's what's bugging me here. Subclass here, PCI get device by vendor. Vendor is an int16. Is it in here? Is somebody using this? PCI driver. It's got to be this stuff here, like the PCI class, subclass. I'm guessing it's this. There's some metadata on the PCI scan that tells you what type of device it is. Like there you've got like information of where it's located, like the bus, the slot. And then you've got this vendor device ID subclass. I bet £1,000,000 if I go back to this OS wiki. I bet that class stuff is all about determining what you're dealing with. Device structure, here we go. Identifies a particular device to manufacturer. The list is here. What is this list? Vendor ID. Oh, that's a massive... Okay, that's just a mapping of the vendor ID. Let's see, status... command, class code, a read-only register that specifies the type of function the device performs. Sorry. Command register, interrupts, status register, header types. Base address register. Oh, that's what the bar is. It's the base address register. Where have we seen the word bar? Here we are. It's the class code. So using the class code and the subclass code, you know if you're dealing with a graphics card, a old style SCSI, an IDE controller, floppy disk, RAID, an ATA drive, serial ATA, network cards, ISDN controller. Yeah, because I bet you can plug modems into PCI. What else is there? 3D controllers, audio devices, flash and RAM controllers, because you can probably put RAM extensions into a PCI Express slot or something. What else is in there? Serial controller, parallel modems, network cards. System peripherals. God, this is a hell of a lot of stuff. Again, writing a full massive OS where you'd want to, distribute it all over the world and support all the different types of manufactured devices that can be plugged into a motherboard, you would probably be spending a lot of time writing support for all of these different device types. But we're beelining to just finding the disk drive, right? That's all we care about. We're going to do the disk drive, and then we're going to do networking, and then we're going to be in a really, really good state. Co-processors, satellite communication controllers, satellite TV controller, wireless chips. They can live on the PCI bus. Needs cat ears on his headset. Do I? All right, anyway, so we're going to have some fun scanning for all of this information. Now, we're probably going to be able to do a big dump of what we find. Like, we're probably going to find a load of devices, and it'll be like we can map them to these string types, these class codes. There are 3 ways to enumerate devices on the PCI bus. The first way is to brute force. The second way avoids a lot of work by figuring out valid bus numbers while it scans, and it's a little more complex as it involves recursion. For both of these methods, you rely on something firmware to have configured PCI buses properly, setting up PCI to PCI bridges to forward requests from one bus to another. The third method is like the second method, except that you configure PCI bridges while you're doing it. For all 3 methods, you need to be able to check if a specific device on a specific bus is present and if it's multifunction or not. So some devices actually are multiple of things. So you might have a device connected on the PCI bus that says, I do graphics and audio and networking. And then you're like, oh, shit. So it's not just a one-to-one device thing, it's a one-to-many device thing. And that's the brute force scan over 256 device checks. 32 devices per bus, 256 buses. You know what? If it's not expensive to parse that information, why wouldn't you just brute force it? I bet it's expensive. I think the scariest thing about that whole scanning was that you can have PCI bridges. So a bridge that can carry a different set of PCI devices. Like, I don't know if I've never seen this before, but can you put like an extended PCI bridge in a motherboard that gives you another 4 PCI Express slots? Talking to a GPU sounds insanely fun to think about, but it's one of the most insane things to even think about because It's an operating system in itself. So like we're creating a kernel that lives on top of an x86 64-bit processor to create an operating system. And then connected in your machine is a GPU that would also need a kernel and plugging into your operating system. And the problem with writing kernels for the GPU chips is that it's all closed information. I think the best, if I was to honestly do it, the most resourceful route I can think about is probably checking the SDL source code and seeing how it initializes OpenGL. And then possibly finding some OpenGL source code and seeing how they talk to the device. And maybe, just maybe, you might get some joy from that. But I wouldn't even dare to think about the effort that would take. I'm doing a GPU driver. And it's kind of sad, really, because for an operating system, it's really, really slow to modify the screen data in software. So like non-hardware supported screenwriting and reading is horribly slow. Like disgusting. It's so much so that you just don't want to do it. Right? You don't want to create a Windows system in a software UI. It would be so buggy and slow. I think, actually, I'm talking out of my ass a little bit. You do have good documentation around the Intel graphics chip that lives on the motherboard, which is a graphics processor that is not part of the GPU. Obviously, most people are aware of the Intel integrated VGA chip that lives on the board. Now that thing is quite well documented, and it's even on OS Dev. So if you want to go to, let's find it, video, accelerated graphics card, native Intel. Here we go. So you could create a driver over the Intel integrated chip, and then you've at least got a bit of hardware acceleration maybe for your UI. Like if I was serious about creating a UI for an operating system, I would definitely do an Intel graphics driver. Like you wouldn't do it in software. Yeah, and pointing you here to like there's even Intel display.c in the Linux kernel that you can probably rip some stuff from. So yeah, I mean, another option, right? If you're gonna want to do a bit of UI, you can do the Intel chip. So back to this scanning then. IRQ handling. If you're using the old pick, your life is really easy. You have the interrupt line header field. Well, we're not using the old pick. We're using the IO pick. Thing is, it talks here about this being a bit difficult, but we've already done this. We have a CPI scanning in yeah, it's in here. So we scan an area of RAM that reads a ton of like topology and power management and support chips and stuff. So we might just go through the I/O APIC just because we have it all set up. Once you've found the I/O APIC pin, all you do is map that to an IRQ using the I/O APIC redirection table. Again, we have that function written. We can pass in an IRQ number and we can say what vector in the IDT we want that to route down. So we're good. We can do IRQ handling. MSI. Oh, message signaled interrupts. Okay. Message control, message address low and high, reserved mask pending. Per vector masking, multiple message enabled. MSI interrupts seem to be invariably edge triggered high. Okay, that doesn't sound too rough at all. Table offsets in the bar. Table sizes, vector control. Multifunction devices are signaled on bit 7 of the header type field. I love that statement. To detect the number of functions, you need to scan the PCI configuration space for every function. Unused functions have vendor FFFF. Device IDs and class codes vary between functions. Functions are not necessarily in order. You can have function 0, 1, and 7 in use. Yeah, this seems like a really fun thing that we're going to embark on. Scanning this stuff. And then finding our drive. That's going to be the even like at the first cool moment is we found the drive. The drive has been located. And it's like, okay, now how do we talk to it? I am human. Do you speak English? So main quest is find the drive on the PCI bus. I just want to know, just to start my brain off, is where does this journey begin? Where do we start finding this information? Oh, here we are. Configuration space access mechanism number 1. And that's using the out and in instructions, which I think Lyra OS called Legacy. This configuration space access mechanism was deprecated in PCI version 2. The I/O port. Oh, it's using I/O ports. Oh, it's another set of I/O ports. And then it has this one, the memory map PCI configuration space. So I'm guessing you go through the ACPI for this, where it's simply memory mapped to no I/O ports are needed. This access mechanism is described in PCI Express. Okay. Detecting configuration space access mechanisms. All right, let's just go for a little side quest down PCI Express here. And where are we going to get, where's the base address? Where does this live? This extended configuration space cannot be accessed using the legacy PCI method through ports. Instead, an enhanced configuration mechanism is provided. Click. On 88664+, the address of each memory area is determined by the ACPI MCFG table. All right, that is the golden thing that I was looking for. So now we go and pop open the ACPI spec, which is here. Da-da-da-da. And we look for didn't find it. Tables. MCFG, are you in here? There we are. PCI Express memory map configuration. And then you've got to go off and find something in here, I reckon, to MCFG, PCI SIG home, specs. PCI Express base specification with version 6.2. Change bar improvements. Yeah, it might be this guy. Oh, you need to log in? No. Okay, well, oh, it already gives us the table format here, actually. Look, table signature, revision, checksum, OEM ID, yep, standard stuff, configuration space, here we are. Base address of the enhanced configuration mechanism, the PCI segment group number, the start PCI bus number decoded by the host bridge, the end number. All right, so before anything then, let's just see if we've got that in the ACPI. We can just light that up right now. So we'll go over to our ACPI module and let's have a look. ACPI init. Walk the RSDD entries, looking for the APIC entry. IO APIC. Root system description pointer. Here it is. That's where we begin our life. Walk the entries. Yeah, so let's just make a log here. Found ACPI table. All right, yeah, no problem, King. I should be streaming most evenings after work, so you'll probably catch me, I'm sure. And definitely on weekends. But yeah, if we just dump this signature. It's going to be 4 chars actually, because it's not a 0 terminated string. Zero, 1, 2, and 3. Okay. And I can see it already. If I just bring up the log file. So found ACPI table records here, look. So we've got one there, the MCFG. So that guy leads us into finding the base addresses of the PCI Express memory mapped IO registers. And that's when our life begins on writing the PCI scanner, which is here. So once we've got that table passed, cool. And then we're into this check device function, which we can just do a brute force scan to begin with. And then, woo, we'll see if we can find the drive. And in talking to the drive, it's probably going to be, I've still no idea how that's going to happen yet. But we'll see, we'll find out. We'll dig deeper into the documents. So I think that's going to be it for today. It's been a lot of research for our next tasks. So I think tomorrow what we'll do is we'll get that ACPI table passed and then see if we can light up walking down the PCI bus and then reporting on the connected devices and seeing if we can find the class codes and subclass codes that we're after to identify that we've got a hard drive. And yeah, that'll be super fun. Super fun. All right, well, thanks for watching. Let's do an end of day commit. So that's the LAPIC code sorted, which is wonderful. I'm so happy we've got that LAPIC timer done. But yeah, so thanks for watching, everybody, and I will see you in the next one tomorrow, hopefully, around the same time. And thank you, Exploding King, for the sub. You are the founding sub of the channel. Good night, everybody. Have a good evening. Goodbye.